Okay, so this lecture is meant to go through the concept of power. And in physics, power is the rate at which work is done. And the kind of tricky thing is that sometimes I've seen on like the AP tests or on different assessments that they won't outright ask you for the power. They'll say, what is the rate at which work is done in this scenario? And so it's just a fancy way of saying power. The symbol for power is a capital P. The equation for it just comes out of the definition. Power is the rate at which work is done. So it's just work over time. But keep in mind that work could be changed in energy, right? So power could also be equal to a change in energy over time. The units for power, work or energy, are the units of joules. And time is, I was going to say, time is the units of time. That's not right. Time is the units of seconds. So this is joules per second, which is equal to a watt. Okay, abbreviated capital W, and you're like, awesome, another W. Whenever a unit is named after a person, it's capitalized, like newtons is capital N, joules is capital J. So named after James Watt. And that's the same watts that you have like with light bulbs, with any type of electrical appliance. So that's just looking at the amount of electric potential energy that's being converted per second. Now, there's also one other variation of the power equation, and you don't see it that often, but I do want to expose you to it. And it comes out of the definition with work over time. Now, remember, work is also, if I think about it in terms of force, work is equal to FD cosine of theta. So if I took this and plugged it in here, this would be FD cosine of theta over time. And you could kind of combine that. Distance over time, displacement over time is velocity. So this could actually be rewritten as force times velocity times cosine of theta. Again, very rare that you kind of see this scenario, but I think it is on your equation sheet, so I wanted to expose you to that. So let's just do a few examples of power. So this problem says, and I want to show you two different ways to solve this problem. It says a crane hoist lifts a load of 1,000 kilograms, a vertical distance of 25 meters in 9 seconds at a constant velocity. How much useful work is done each second? So there's two different lenses that you could actually solve this problem through. I mean, they're both power, right? But one, we could think of it as power as being work over time. So this FD cosine of theta over time, or power is equal to change in energy over time. And in this case, it's a change in potential energy over time. Okay? So if I think about this, like this crane hoist lifting this load, so I've got this, I'm just going to make it a box because I can draw boxes. I've got 1,000 kilograms, and this crane is like lifting it up. I'll call it the force of the crane, right? And there's the weight of the box itself that is pulling it down. And we're told it's being pushed up at a constant velocity. So if I think about this in terms of forces, the force of my crane has to equal the weight of the load because it's moving at a constant velocity. So the force of my crane is just equal to mg, okay, like to lift it upwards. So if I thought about trying to figure out power, I'm going to call this method 1, method 2. If I thought about trying to figure out the power using method 1, I'd say power is equal to the force of my crane times the distance times the cosine of theta over my time. The force of my crane is just mass times gravity times my distance, cosine of my angle. My force of my crane is going up. The distance it's moving is up, right? 25 meters. So the angle between up and up is 0. And cosine of 0 is just 1, and then divide that by my time. So this is going to become, plugging in values, my mass is 1,000, gravity is 9.8, mg, distance is 25, times 1, divided by my time of 9 seconds. Pause the video, calculate that out. What do you get? What do I get? Oh gosh, I don't even know. I don't have the answer. I didn't solve it. 1,000 times 9.8 times 25. You should have beat me by now. I get, ooh, big. 245,000 watts. I have no room to write W there. Okay? So that's the method of looking at through forces. If I look at the method through energy, you're going to see it's very similar mathematically. So my power is equal to my change in potential energy. So this would be mgh final minus mgh initial over my time. Well, mgh final is my mass, 1,000, times gravity, 9.8, times 25, minus my initial potential energy. My initial potential energy is on the ground. There's no potential energy. This is over 0. Divided by my time. It's the same thing mathematically. So you're going to get the same exact 245,000 watts. Okay? So there's different lenses you can look at a problem with, and either method will solve it correctly. Okay, one last example. This one says an initially stationary 2 kilogram object accelerates horizontally and uniformly to a speed of 10 meters per second. What is the average power exerted on the object? So in this case, power is, we're going to look at it through the lens of energy. Power is equal to the change in energy over time. It is changing kinetic energy. So pretty straightforward. 1/2 mv final squared minus 1/2 m the initial squared over time.